What's up, Pussies? It's your boy Pussy here. We're going to do another podcast. Today is the 5th of September 2021. Yesterday I got my COVID vaccine, and today I'm doing some chemistry work. So let's get right on into it. Let's go! I'm just going to be watching some videos. On organic chemistry. I say yesterday I got the COVID vaccine because I feel like that'll be an interesting thing to be watching this back during this coronavirus time. So right now public testing. Right now the vaccine, it's available for anyone in New Zealand. Obviously, being 17, I'm the last age bracket to get it because I'm the least vulnerable to it. But yeah, I think a week back they made it available for everyone, and my mom was like, "Come on, Flynn, let's go, let's get the vaccine." So me and my mum got the first shot of the vaccine right in my arm. So yeah, I'm coronavirus resistant, except I'm not. I need my second jab, which will be in 6 weeks' time. Anyways, let's get to study. Today, light study, man. I want to be, oh, that's an interesting video. Fuck, why did that pop up? I do want to watch that. Mr. Beast, Extreme $500,000 Game of Tag. Oh, that'll be for that last leave the circle thing, won't it? That's a sick fucking video. I'll watch that in my 10-minute break. I want to do this, been watching some videos on studying, how to study better. Just got this app called Anki. Apparently spaced repetition is really important. That's what fucking everyone goes on about. All the videos that I've watched, meaning that every couple of days you're learning something, and then you've got these flashcards with this app on Anki. You write in flashcards, and you practice those flashcards, and you've got a deck, and it just instantly, you've got your Anki work, and it's like an algorithm. And knows exactly what cards you should be studying, yada yada. So every couple of days you get the same cards so that you can kind of really get in your head that spaced repetition to really get the shit nailed down that you're learning. So I want to be using those for chemistry. So I've messaged my chemistry teacher asking if she's got any flashcards for the externals. So right now I'm just doing this internal for chemistry, which my teacher's roasting me about. I'm not doing too good at. But there's not too much for me to study. I kind of understand everything basically. I reckon I should be able to get a mirror on that internal. But I've decreased my hours at work. I now only work 2 days a week. So I've got heaps of time to study and heaps of time to focus on my business, my dropshipping brand. So I'm going to be studying a lot more. So I want to really get those externals down for chemistry, which will help me in engineering next year. Anyways, let's watch some organic chemistry videos. That video was uploaded 30 minutes ago. It has 1 million views on YouTube, which is very good. That Mr. Beast video. Crazy, bro. NCA level 3. Let's start that timer, huh? I'm just watching random ass videos on this. Fuck it. I won't really be learning anything. I'll take a couple notes, but barely any notes. Just kind of they do this thing on a lot of the studying videos that I've been watching, where they go into a lecture beforehand, they revise it so they kind of get a basic understanding of shit. Then they go and then they really try to understand it, get the flashcards, and then use Anki to really get that nailed down, that spaced repetition. So I'll do that practicing it, just kind of getting the basic knowledge of organic chemistry down. Because fuck it. Got a little timer here that the student uses, 50-minute timer for a 10-minute break. And we start the timer.
Hey guys, I'm Penny, this is Fraser, and this is the Level 3 Organic
This isn't going to
Strategy
be much
video.
talking in this podcast. That dude's ugly as fuck, Jesus Christ. But, yeah, these podcasts are pretty shit right now. Even what I want out of the podcast, at the basic. Dude's dog just ran out. What the fuck's going on? Even for the basics of just recording myself almost as like a journal, so I can look back on. These podcasts aren't the best. It's mainly just me talking for a little bit, then not talking for ages, and then maybe talking for a couple minutes randomly when something pops into my head. But again, I'm not going to put much effort. I might actually put a bit of effort into this soon. Now that I've got time, got heaps of time to do stuff. I'm only working 2 days a week.
This standard is broken into a few key parts. We got naming, isomers, melting points, boiling points and solubility, esters, reactions, and polymers.
While you can expect specific questions in all these areas, expect questions on reactions and naming to pop out throughout the paper.
So reactions is a big thing that people freak out about organic chemistry. They think it's all about memorization. They have to remember 200 different statements about like alcohols and PCl3 going to haloalkanes, but it doesn't have to be like that. Humans don't really think well when you have these big outlined, reaction flow charts that take up a whole page. Humans think really well in lists. So it's really a good idea to organize your thinking in sort of a list way. And the way to do that for organic chemistry, in my opinion, is to do that with types of reaction. So there are 5 types of reaction you need to know at level 3 organics. There's addition, elimination, oxidation, reduction, and substitution. So if you go through and learn a bit about each of this different type of reaction, then you can, whenever you're confronted with a reaction, you can, cross it off the list. So for example, addition reactions, you break a carbon-carbon double bond. Elimination, you form a carbon-carbon double bond using sulfuric acid or KOH alcoholic. Oxidation uses permanganate or...
Addition. So I'm just going to write the basics, eh? This is all ringing a bell, by the way. I did this. This is very similar to level 2 chemistry, which I did not last year, but the year before that. I actually started taking level 3 chemistry and then I dropped it for level 3 history. I can't remember why. I genuinely cannot remember why. Why did I drop it?
Dichromate, reduction uses NABH4 and reduces the number of bonds.
Okay, so we're doing fucking oxidation reduction in this shit. What the fuck? Alright. Oh yeah, I just fucking wrote that down. Oxidation reduction and substitution. Addition, elimination, oxidation reduction and substitution. What the fuck?
So oxygen and substitution is all about swapping. Obviously, this is just a very brief overview of that thought process. Definitely go ahead and check out the study time level 3 organic walkthrough guide, because that details this process a lot more in depth.
There's very likely going to be a question on esters in the exam, and I have some good news for you. It's pretty much the same from year to year. All you can do with esters is make them or break them. To make an ester, you need a carboxylic acid and an alcohol, a little bit of acid as a catalyst, and some heat. Don't forget that water goes off as a byproduct. To break them down, in both cases you always need water. However, there's 2 different types of hydrolysis. There's an acid hydrolysis and a basic hydrolysis. In acid hydrolysis, you end up with the same alcohol and the same carboxylic acid. However, in basic hydrolysis, you end up with the same alcohol again. However, you get a carboxylate ion, and that's essentially just the conjugate base of the carboxylic acid.
Just like the esters question, it's very common to get a question on enantiomers in level 3 organics. So the first thing that you need to know about enantiomers is how to identify the chiral carbon. And that's just the carbon with 4 different groups attached. Then you need to know how to draw the enantiomers in 3D, like this. And basically, enantiomers are just mirror images of each other. Then, the last thing you need to know is you need to say how you can tell enantiomers apart. And for this, you can just throw out this sentence. Enantiomers rotate plain polarized light in different directions. Don't need to understand what's going on. Don't need to understand what that is.
I'm just gonna like jot down this word. Enantiomers. What the fuck? How the fuck do you say that? Enantiomers. Enantiomers. Rotate. Plain polarized. What the fuck? Yeah, how crazy is this shit, eh? How crazy is this shit? These people are fucking idiots. They teach you how to pass the exam. They don't teach you what the fuck it's useful for. It's crazy, eh? Their whole goal is to get you to pass the exam, not even to retain the information, just to pass. Like, what the fuck? It's going to be very useful for you to retain information. It's like, oh, just remember this one fucking sentence. You don't even need to know what the fuck it means. Like, Jesus Christ. Who the fuck runs NCEA? And generally, that's people's thought process as well. They're just like, I want to learn this so I can pass the exam. That makes sure that I know this, and then I can forget it. Even though the whole point of the exam is to make sure that you know that, because you're going to need that. Fucking crazy. You're going to need the information for level 3 chemistry, so that it can help you with your future career in level 4 chemistry, or university chemistry, whatever. But the way they run it, it's like, oh, just remember this for the test. Then you can fucking forget it as soon as you leave the test. Like, no, you're gonna need that information for fucking level 4 chemistry, and you're gonna need that information for level 5 chemistry, and you're gonna need all that information for your fucking job that involves chemistry.
You can just write that and you will get the marks.
Another common question that you're going to get is on reflux versus distillation. It's important to be able to understand the different apparatus between the two processes and to be able to pick them out of a lineup. It's also important to understand what happens to a primary alcohol when you react it, how it goes into an aldehyde and then a carboxylic acid. In distillation, you're going to be separating different compounds based on boiling points. So when we have alcohol and we react it, the aldehyde evaporates and it's then condensed out into a separate vesicle, so you're able to separate that aldehyde. In reflux, you evaporate it and it's condensed back down into the same vesicle. So then the aldehyde reacts again into a carboxylic acid. This way you're able to react the alcohol completely into a carboxylic acid.
Overall, everything comes down to naming and reactions. These won't be localized to specific questions like esters or polymers, so it's really, really important to have this and know that they're going to come up throughout the whole paper.
While we've covered some important strategies, note that we haven't quite covered everything. It's important for you guys to do at least 3 to 4 exam papers, check out the study time walkthrough guides and our checklists so you can be better prepared for the exams.
Thanks for watching and good luck in your organic chemistry exam.
Okay.
Welcome to this video on reaction scheme.
Learn coach. This guy's fucking crazy. I remember I used to do learn coach when I was doing level 2. I remember this one time where it's like, his video, it's like, he fucked up 4 times, and instead of cutting it, he just left that shit in, like, it was like this. He had the thing that he was doing, and he was like, and so this, and then refresh the screen. He was showing something on the screen, like a reaction, said, and so this reaction is, fucks up, and he's like, and then he just like, takes the screen back to white, and then he goes, and then he shows the reaction again, and he goes, and so this reaction, fucks up, does that 4 times, and he's like, he like fucks up, and like, on the last time he's like, oh shit, and then that's when he cuts the video. That is when he decided to edit the video there. But you know what? Learn coach, I love you.
Now on level 3 organic
you,
chemistry, you learn so many different reactions. Reaction schemes is a way to bring together all of the reactions you've learned in organic, both from level 2 and from level 3 into one type of question. So in this video, there's actually no new information, but it brings together all of the previous information you might have come across. So let's quickly recap the reactions from level 2, the important ones we need to know. The first is addition reactions. And these happen from level 2 when we broke a double bond, and this is a fast reaction. So it started with an alkene, something with a double bond. And the key ones we learned were hydration, where you add an H2O. So this is where you break open the bond, one of the OHs adds on, one of the H's adds on, so you create an alcohol. Then you learned hydrogenation, where you add hydrogen on. So this turns an alkene with a double bond into an alkane, something that would have all H's around there. Then we learned about halogenation, where you break open this double bond and add on a halogen, almost always Br or Cl. And finally, we learned about Markovnikov's rule. And this is where the rich get richer. So the important thing is there'll be a major and a minor product produced. For example, when we add on a halogen. Now, you're trying to decide which carbon the H will attach to. It's the one that already has the most H's. So if you're unsure on any of this, go back and watch the level 2 videos on addition reactions. Now, also we learned about elimination reactions. Now, this is going back from an alkane towards an alkene. So specifically, we needed a reagent to make this happen, which was H2SO4 or sulfuric acid. And the examples were often an alcohol, something with an OH going back to an alkene, and that would have water produced, H2O, because you'd get the OH and the H joining together when you created this double bond. And you could get haloalkanes going back to alkenes. So instead of an OH, this might be a Cl or a Br. Now that would get kicked off along with another hydrogen, and that would create HBr or HCl. So these are the important reactions you need from level 2. And from level 3, we learned some oxidation reduction reactions. The important ones were a primary alcohol going through to an aldehyde, then a carboxylic acid, and we used the oxidizing agents of acidified permanganate and acidified dichromate to make that happen. In the same way, they would oxidize a secondary...
Acidified manganate and acidified dichromate. We use those a lot. MnO4 minus, KMnO4. And Cr2O7 minus, 2 minus. Oxidation number -14, -16, so +8. What? No. Oh yeah, what the fuck? Oh no. The other way around. +6. -17, -14, so +7. Yeah, no, it's plus. +6. Yeah, it's +6.
Alcohol. That would go through to a ketone, but then couldn't be oxidized anymore.
What the fuck's a ketone?
When we learned about reduction, we learned that aldehydes could be reduced back to a primary alcohol. And we'd do this using sodium bromohydrate, or NaBH4. Now, this sodium bromohydrate would also reduce a ketone back to a secondary alcohol.
Sodium bromohydrate.
Well. And remember, if you're ever using these oxidizing agents, you're going to see a color change. Finally, in the second video, we learned about a whole bunch of reactions between acyl chlorides, esters, amides, and carboxylic acids. So you've got a list here of an acyl chloride, which will go through to carboxylic acid or an ester, a primary amide or a secondary amide, and what you need to react this acyl chloride with. So you need to be familiar with all of these reactions because they could all come together in these exams. So now we're going to go through a typical question you might encounter in your exam. So this is something like, propene can be reacted with water in the presence of acid to form a major product called A and a minor product called B. And then you're going to see a list of instructions and this big reaction scheme diagram. So you're starting with propene, which can be reacted with water.
Yeah.
The presence of acid to produce a major product here, product A, and a minor product, product B. So this is going to be Markovnikov's rule. Then you'll go on with more instructions. So B is oxidized to form D, A is oxidized to form C, D reacts with SOCl2 to make E, E then reacts to create product F, D can react with G when you have alcohol and concentrated sulfuric acid, or it can make ester H when you mix it with alcohol A rather than alcohol B. So all of these steps are laid out and shown in this diagram, and your job is going to be to identify the reagents that happen if they're not listed, and what all of these products A, B, C, D, E, F, G, and H are, as well as drawing the structural formula of these compounds. So you really need to understand all of the reactions to pull them together in a question like this. So we're going to go through this question so you can see how this would take place. So first of all, the important thing is you start with propene. So propene has 3 carbons and it has a double bond on there. Now the important thing is it goes to a major product.
Remember that. Oh yeah, "ene" means it's a double bond. Pro means it is 3. No, I don't remember how to name products. Fuck me.
Product, which is A, and a minor product. Now, this is Markovnikov's rule where the rich get richer. And what it means is that when you add on a hydrogen, when you break open this double bond, the hydrogen is going to add on to the carbon, which already has the most hydrogens attached because it's the richest. So here you'll notice that the carbon on the left has 2 hydrogens attached. The carbon on the right only has 1 hydrogen attached. Therefore, the major product is when hydrogen attaches to this first carbon here. So this is an addition reaction where it opens up the double bond, and that first carbon will get an extra hydrogen attached, so it becomes CH3 rather than CH2. The OH group from water will then get added onto this middle carbon here, so it'll be COH. It'll still have 1 H attached to it because it's got this extra bond open to it. And then we still have this CH3 out on the right-hand side here. So that's the major product where the rich get richer. Now, that doesn't always happen. Sometimes you get the minor product as well, where the hydrogen actually attaches to the carbon with the least number of hydrogens. It doesn't happen as often, but it does still happen. So that would mean you'd break open this double bond where the carbon on the outside would get the OH group attached. Now, it doesn't happen often, but it does happen. So here we've got the carbon on the outside with the OH group attached. We've flipped it around. And you'll notice that this has 2 H's, so CH2 and the OH attached to it. And this middle carbon is CH2 as well. It's got its original hydrogen plus another hydrogen that's been added on from this open bond. And then there's still CH...
No, I'm not understanding this. It's actually Father's Day today. We had pancakes. My mum was freaking out because she fucked up the pancakes somehow. She was having a bit of a shitty morning. I don't think she got much sleep, and her arm was actually hurting from the coronavirus vaccine, and my dog took a shit inside. Damn it, Jazz. And the pancakes were getting fucked up, so she was kind of like having a bit of a cry. Getting a bit pissed off. And I ended up having 5 pancakes. 5 pancakes. I can never do that when I'm bulking, but now that I'm not bulking, the meals that I have, I'm easily able to have. I have a lot less meals, but the meals that I have, I can eat a lot more.
CH3, which
is pretty fucking common sense. Don't know why the fuck I'm trying to explain this. Like, it's fucking level 3 chemistry, level 3 organic chemistry, where the example question is propane can be reacted with water in the presence of acid to form a major product A and a minor product B.
Comes off from down here. So this is an addition reaction where you need to follow Markovnikov's rule to get your major and minor products. Now that we've done that, we can look at what happens to both A and B. You notice that product A, which we've named as propan-2-ol, because it's propanol and the OH group is on 2, versus propan-1-ol, where the OH group is on carbon number 1. So they can undergo oxidation. If you want to oxidize here a secondary alcohol, you're going to get a different product if you try to oxidize a primary alcohol. So let's look at the oxidation reduction reactions we already know. So here we've got a primary alcohol gets oxidized to an aldehyde, then to a carboxylic acid, whereas a secondary alcohol gets oxidized to a ketone. So if we go back here and let's look at our secondary alcohol, our propan-2-ol. Now, if we want to oxidize that, what's going to happen is you're going to kick off one of these hydrogens here and another hydrogen from the carbon, and you're going to get your double bonded oxygen creating a ketone. Now, this can't be oxidized anymore. So product C as a ketone would be called propanone. Now, if you're going to oxidize a primary alcohol, you'll get something different. So product D is where you get a carboxylic acid. Now you might ask, how do you know that it's not an aldehyde? The trick is, we've only learned one reaction from an aldehyde. It gets oxidized onto a carboxylic acid. Whereas if you look at product D, you'll see that it goes on to create an ester, another product E, which is completely separate as well, under SOCl2. None of these are aldehydes being oxidized to carboxylic.
Fuck this video.
Welcome to this video on naming organic compounds.
Fuck it. Oh.
Greetings everyone, welcome to this particular video.
Nah, that kid seems too nerdy. Alright, let's just watch this video.
The first thing you need to know is that level 2 material is incredibly important for level 3 organic chemistry. And right throughout the organic chemistry topic, we're going to be referring back to the level 2 content that you should have learnt last year. In this video, we're going to be covering naming organic compounds and isomers. So at the start of each point, I'll briefly touch on what you need to have known from last year. So to start off with naming organic compounds, at level 2, we learned all the prefixes which get matched up with the number of carbons. So for example, one carbon has a prefix of meth, We have 5 carbons have a prefix of pent, and so on. These are all listed in the table here. Now, while this prefix dictated the number of carbons, how those carbons were bonded together and what extra molecules were added on is what type of compound it was. So that's how these 7 different compounds came into play. And for each one of those, we needed to know the structural formula, how the atoms were actually bonded together, the molecular formula, what atoms were actually in the whole molecule as a total, and how to name it. So this might be how to name alkanes or each individual type, but also, as we can see in this example, how to name combinations of these compounds. So this is what we needed to know from level 2. Now, if you're not familiar with all of this, do go and see the level 2 chemistry videos on organic naming compounds part 1. But at level 3, we're going to look at 5 new compounds, and every single one of these compounds will have a carbon with a double bonded oxygen attached to it. And you might know from level 2 that we've actually seen one compound that has this all.
Get some new creative shots, and I'm going to shoot them.
Ready. So this is the carboxylic acid. Now, carboxylic acids have that structure where you have a chain of carbons, there's a double bonded oxygen attached to the last carbon, and a hydroxyl group or an OH group attached as well. Now, we're going to use carboxylic acids as an example to learn a little bit of notation before we get into this. The first of 2 that you need to know is R. R just means a chain of carbon atoms. It could be any length, doesn't matter what it is. So in this case, we know that we've got the critical ending of a carboxylic acid because it has the C double bonded O and an OH attached to it. And then we have R, some length of carbon atoms that comes after it. Doesn't matter whether it's 2 or 5 or 10 or 10,000. It just means some length or some chain of carbon atoms. So that's what R means. The second thing we need to know is the Z group. And the reason we have this is because every one of our new compounds has a carbon with a double bonded oxygen. So the only thing that changes is what's on the other bond of the carbon atoms. So this Z group is going to be the focus of everything we're doing for our new compounds. And for each of those compounds, we're going to cover the structural formula, how the atoms are actually bonded together, how to name these new compounds, how to write out their molecular formula, what atoms are actually in there, and their general formula. It's the same as the molecular formula, but it will include this R, meaning that you could have any length of atoms in there, not just one specific example we've got listed. So to put these all out there, we've got 5 new types. And every one of these types, you'll notice, has a dash CO to start with. And that's because we've got a dash C with a double bonded O all of the time. It's just the Z group which is changing. Now Z isn't actually an atom, it's just a name for whatever else could go there. So in the case of a carboxylic acid, that was a hydroxyl group. With an acyl chloride, that's a chlorine group. For an ester, it's an oxygen and another chain of carbons. And so on as we go down the list. We're going to cover these one by one. So the first example we want to look at is acyl chlorides. For this, the extra Z group is a chlorine atom. So a structural formula could look something like this. We've got a chain of carbon atoms, and the N one has the C double bonded O with a chlorine attached for the final bond on a carbon atom. When you're naming this, the prefix will come first of all from the alkane you have at the start. So this is ethane because it has 2 carbon atoms. But instead of the E at the end, we rename it oil chloride. So combining those together would give us ethanoyl chloride. So that's how you name acyl chlorides. Some of you may come across the name acyl halide. This includes any of the halide atoms, or in our case, most commonly bromine. But for your level 3 exams, acyl chlorides are the only ones that are going to come up. Next, we can write out the molecular formula for this one. So we've got our CH3 group, and judging from this table, we've still got our COCl group that we put on the end all the time for the molecular formula of acyl chlorides. Finally, our general formula just replaces that extra chain of carbons, in this case just that one extra carbon, with an R. But we keep the ending, which is the COCl, a common ending on any molecular formula, so that we can know it's an acyl chloride. Now let's look at esters. The Z group on an ester is a little bit different. It has an oxygen, but because oxygen can have 2 bonds, it bonds to another chain of carbon atoms. And you'll see that because we've got our original R, some chain of carbon atoms. We've got another down here, which is another chain of carbon atoms. The dash up here just means it's different from the first chain that we had. So an ester uses a carbon and 2 oxygens to bond together 2 separate chains of carbon atoms. So a structural formula could look something like this. Here we've got a chain of 3 carbon atoms, which includes our double bonded oxygen, and that's attached to an oxygen, which is attached to another carbon chain, which is only 1 carbon in length. And in order to name that, we need to know that we're going to have 2 carbon chains, and we need to name them separately. So to start with, you name your secondary chain, which is the one without the double bonded oxygen. In this case, we've got a methyl group, and we end it with YL, which is methyl. And then the secondary part of the name uses your main chain, which is attached to the double bonded oxygen. In this case, we've got 3 carbons in here attached to the double bonded oxygen, and that's prop as its initial name. And we end it with NO8. So the full name for an ester would be methyl, because it's the first small chain, propanoate. So the molecular formula for this one would be the 2 carbons and the 5 hydrogens out here.
Yeah.
We've still got our COO, and then we list the molecular formula for our secondary chain, which is just CH3. Now the general formula for this, you've got 1 chain of carbon atoms, your R, you've got your COO, which you'll write in the middle, same as up here, and then you do your secondary chain of carbon.
Ester compound. R COO R dash.
Carbon atoms, which in our case was CH3 for our example. So this is esters, where we have our double bonded oxygen, a single oxygen, holding together 2 different carbon chains. Next one we're going to look at is an amide. Now an amide Z group is NH2. So we could do one example for this one here, where we have a chain of 4 carbon atoms, our double bonded oxygen, and our NH2 group attached, replacing the Z group here. So how we name these ones is we add amide on the end of the name of the chain. So 4 carbon prefixes is bute, and then we add amide. So it's butamide as the name.
Yep.
And the molecular formula for this one up here, we've got our 3 carbons and 7 hydrogens on the extra chain. We've got our CONH2 on the end one here. And a general formula of R, because we could have any length of carbon out here and we'd still have an amide, and CONH.
Amide compound. R conha. CONH.
Just 2 on the end there.
Cool beans.
Now one thing that's a little bit different about an amide is we can have primary amides, which only has these hydrogen attached, but instead of a hydrogen, we could actually replace it with another carbon chain, say down here. This would be called a secondary amide because it has 2 carbon chains on it. Or we could attach a 3rd carbon chain, and that would be called a tertiary amide. But as long as it has a C double bonded O right next to an N, it is still counted as an amide group. So when naming things in your exams, you'll only be asked to name a primary amide. At the most, you'll just be asked to identify an amide group if it's a secondary or tertiary one. Next is an aldehyde. Now an aldehyde's a little bit different in the fact that up until now, we've got atoms that aren't just carbons and hydrogens. We've got a hydroxyl group, chlorine, oxygen, an amide group. Now we've just got an extra hydrogen attached onto the end as the Z group. So it makes it a little bit more subtle. So a structural formula could look like this. A chain of 4 carbons, your double bonded oxygen, just a simple hydrogen added on the end. So this gets the prefix at the end, despite the misleading spelling of anal. So the prefix for this would be bute, adding on anal, makes butanal. And once we've done this, the molecular formula, we've got our 3 carbons and our 7 hydrogens, plus our COH, which is the extra part we add on to the molecular formula at the end. And as a general formula, we'd replace those 3 carbons and hydrogens up here with an R. So that's how we do aldehydes. Now, one thing to know with an aldehyde, the double bonded O is always on the end. Because if it's not on the end, we give it a different name, which is called a ketone. That's the next one here. So a ketone just continues on the carbon chain. And you'll notice it's not a different carbon chain. I haven't labeled it R dash. It's the same carbon chain that carries on. Just one of the carbons will have a double bonded oxygen attached to it. This is called ketone. And when you're naming it, it has its normal prefix and "-one" at the end of it. So if we look at a structural formula like this, again, while it looks like we have a chain of 4 here, which would be bute, it actually is a chain of 5 because this carbon chain carries on down. So here we have 5, which is pentan, and then we add on the ending "-one," which gives us pentanone. So the molecular formula here would be still C3H7, because we still need to label the C double bonded O separately. Then we have CO, And then our second lot of carbons, which in this case is just CH3. And as a general formula, we have RCO, and it could be R dash or just a regular R. But we've got 2 chains on either side of the CO when we're actually writing it out as a molecular formula. So these are the 5 new different types of molecules you've learned for level 3, in addition to all of the level 2 molecules that you still need to know. And remember, it's the Z group, which is always changing because every single one of these new ones has a C double bonded O attached to it. So we can break these up roughly into 2 different categories. We've got all of the ones up the top, which have interesting endings replacing their Z group. For example, a hydroxyl, a chloride, an extra oxygen and chain of atoms, an amide group or NH2 group. These are called acid derivatives, and they all act really similarly to each other. They have very similar properties. Compared to when we just have our regular hydrogens and carbons down the bottom here, they act similar to each other, but very different to this top group. Now I'm pointing this out because later on, this top acid derivative group will react very similarly to each other, but very different to the aldehydes and ketones. So just be aware that if you're talking about these new atoms and your Z group is not just a carbon or a hydrogen, then all of those things are going to have really similar properties to each other. We'll cover that in a future video. But for now, let's go to part 2, where we're going to look at isomers. Now, to briefly touch on last year's stuff, you need to remember that isomers are compounds that have the same atoms, but they're actually arranged differently. So down here, in both cases, we've got 3 carbons and 6 hydrogens, but they're arranged and structured differently. So they're called isomers. Now, there's 2 different types of isomers we learned about: structural isomers, which are also sometimes called constitutional isomers, and this is just when things are structured differently, and geometric isomers, and this only happens in alkenes or alkynes, things with double or triple bonds. And that's because this bond isn't flexible. So you either end up with 2 groups on the same side, which is called cis, or on opposite sides, which is called trans. These are geometric isomers, sometimes called stereoisomers. Now, if you don't know this or you'd like extra details on this, go to the Level 2 Organic Chemistry video on naming compounds Part 2. This covers isomers in detail. But for now in Level 3, we're going to learn about 2. This covers isomers in detail. But for now in Level 3, we're going to learn about 1 new type of isomer called an optical isomer. Sometimes you'll hear it referred to as an enantiomer as well. So an optical isomer is one that is a mirror image of itself. And this will only happen when we have 1 single carbon that has 4 different groups attached to it. So for example, if we look at butane-2-ol, here we've got 1 carbon and 4 different groups. None of them are the same. So if we write that out in a 3D diagram, and those of you who remember structure and bonding from level 2 will know that if you do this and you hold this up to a mirror, you're going to get the reflection of it here. Now the reflection and the original one cannot be superimposed over the top of each other. They are structured differently and they are not the same molecules, despite being incredibly similar. It's like your right hand and your left hand. They're mirror images of each other, but they're not exactly the same. That's what an optical isomer is. And remember, it only happens when you've got 4 different groups around 1 carbon atom. Now, a question that comes up all of the time is, how do you tell the difference? And surprisingly, they have exactly the same physical and chemical properties. However, the difference between them is that they will rotate a plane of polarized light in different directions. Now, what that means is you get a plane of light or a sheet of light, you shine it through a whole lot of 1 type of isomer or 1 type of enantiomer, and it will rotate clockwise. You shine it through the other type of enantiomer, the other type of optical light, and it will rotate clockwise. You shine it through...
Oops, our 2 meant to say equal in opposite directions, not different directions.
...through a whole lot of 1 type of isomer or 1 type of enantiomer, and it will rotate polarized light in different directions. Now, what that means is you get a plane of light or a sheet of light, you shine it through a whole lot of 1 type of isomer or 1 type of enantiomer, and it will rotate clockwise. You shine it through the other type of enantiomer, the other type of optical isomer, and it's going to rotate it anti-clockwise, the opposite direction. So while they have the same physical and chemical properties, you need to know how to tell them apart. It's a question that comes up all of the time. You need to say that they rotate that plane of polarized light in opposite or different directions. So that's what you need to know for optical isomers. So here's what you need to know overall from this video. The first thing is what we covered in optical isomers, that they are mirror images of each other, and it only happens with 1 carbon atom attached to 4 different groups. They have the same physical and chemical properties. However, the sentence you must remember is that they rotate a plane of polarized light in different directions. That's optical isomers. And at the start, we covered our 5
Hey.
new compounds. And remember,
That's what that other
they
guy
all
said.
had some chain of carbons, the R chain, where the end carbon had a double bonded oxygen, and then some other group we called the Z group. Now that's different for every different type, and we already knew the carboxylic acid group, which had an OH or a hydroxyl group attached to it, but we learnt the new acyl chlorides, which has a chlorine group attached to it, and how to name those. We learnt esters, how to name them, and the fact that the Z group is another oxygen, which then attaches to a whole nother chain of carbons. And when we name that, remember, we name the carbon chain which does not have the double bonded oxygen first, and the one that has the double bonded oxygen second. For amides, we learnt that the Z group is an NH2. For aldehydes, we learnt that it has just a simple hydrogen on the end here. And a ketone is almost exactly the same as an aldehyde, but instead of this double bonded oxygen being on the very end of the chain, this double bonded oxygen was partway through the chain. So that's a ketone. And they loosely fall into 2 different groups where all of the acid derivatives, which are the ones which have something new attached to the Z group, all react really similarly to each other, whereas aldehydes and ketones with just simple hydrogens and carbons react very differently to that top group, but basically the same as each other. So we'll cover that in future videos. Let's look at some questions now. For this first question, we've got the structure of aspartame given here. This is often used as an artificial sweetener in drinks.
What's up? The fuck is that? Oh, I can do that. Oh, well, I can't remember them. Isn't that an ester? Is an ester... Yeah, that's an ester. 4 is an ester. 3 is an what's it called? Amide. 2 is also an amide. Oh, wait, no, that's just the NH2 one. That's from last year, I can't remember. And that one is the simple one. Yeah, that's actually pretty easy.
Drinks. We need to identify the 4 different functional groups here that are circled and numbered and put them in this table. So, one by one, starting with the first one, we can see we've got a C double bonded O, so it's one of our new molecules, and an OH group attached, a hydroxyl group. So instantly we know it's a carboxylic acid, or some of you may have learnt this as a carboxyl group. For number 2, when we look at that, we've got an NH2 group. Now, it's very tempting to call this an amide group because we've just learnt that one. However, the carbon does not have a double bonded oxygen attached, so it's not an amide. It's in fact an amine group attached onto the end of this. For number 3, we can see we've got another NH
Here we go,
down
that's
here,
an amide.
and that is attached to a carbon with a double bonded oxygen.
Easy.
So that one there is an amide group.
And then this one.
And number
is an
4,
ester.
looking at this one, we've got a carbon with a double bonded oxygen.
question.
That
Easy.
goes to another oxygen which attached to another chain of carbons. And if we remember, that one's called an ester. So that's how we do the first question. In the second question, we need to complete this table by drawing our structural formula for these named compounds.
Propanols, that's 3, and that's all propanol, so this is an alcohol, so OH, chloride. So that'll just be 3 C's with a double O bond and a little Cl down there, down in that bitch. 3 bromopentane to own. Okay. So bro, that's 4 in it. Bunt, bro, or is that 5? I don't know. Let's just watch that.
So to start with, let's look at these. We've got propanoyl chloride. Now, the first thing we can do is do the main chain of carbons. Propan means that we've got 3 carbons, so we can draw those ones out.
Easy.
Then oil chloride is an acyl chloride. So it means we're going to have this double bonded oxygen at the end and a chlorine as the extra atom. So that's everything extra. Now we just add in hydrogens to make sure that every carbon has 4 bonds completely. And that is what your structural formula would look like.
Cool.
For the second one, we've got 3 bromo pentane 2 one. So looking at this, the key chain of carbons is pentane. And pentane means we've got 5 carbons in the chain
bromo,
altogether.
that's bromine. Pentane, that's 5.
The next thing you'll notice is it ends in -one. That means it's a ketone, which it just has a double bonded oxygen on one of the carbons. And it says here it's the second carbon because it's 2 one. Then we go to the final part, which is 3 bromo. So 3-bromo just means on the third carbon along, you have a bromine atom attached. So we can add that one on as well. Finally, we can add in the hydrogens so that all of these carbon atoms have 4 bonds each. So adding those on, that gives us our final answer. And finally, we can look at 2-methyl-butanol. Looking here, we've got our key chain as but, which means it's got 4 carbon atoms. The next thing we'll notice is it's got an ending of anal, which means it's an aldehyde. And an aldehyde means we've got the double bonded oxygen and a single hydrogen attached. It's one of the new ones we learnt in this video. Finally, we've got 2-methyl at the start, something we covered at level 2. So 2-methyl means on the second carbon atom, we have a methyl group attached. And with all of these new compounds, you want to count from the end that has the double bonded oxygen. So we go back 1 to number 2 carbon and add on a methyl group. Finally, like always, we'll fill up these carbon atoms with as many hydrogens as we need to get them up to 4 bonds each. So this would be your final answer for that part of the question. And this is how you name the additional compounds at level 3.
Cool. Alright, that's my study done. I'm going to pause this and I need to take those shots for my creatives. I need to take some camera shots. Where did I put my phone? I have no idea. I'm going to take some creative shots with that little shock lock, that little portable door lock, and then we're going to do some more physics. Let's just plan out the shots first. Sucks that screen went, and at the perfect time when my mouth's open and I'm looking like a dipshit. Keel. Let's go to docs and let's plan out these shots. Okay, that's it for the podcast. Anyways, peace out, homies. What the fuck? The screen changed, but it's still where I was before. Anyways, peace.